Hello, Doc.
Hello,
Hey, how are you?
I'm good. How are you?
I am doing well. Thank you for taking time today.
Sure, of course. Thanks for the invitation.
So maybe, do you want to try sharing your slides once?
Sure. So this talk is recorded.
Hey, yeah, is that okay?
Yeah, that's fine.
Okay.
So who will be the audience of the talk?
Mostly graduate students.
Okay.
Yeah.
So
Sometimes and
disabled
yeah.
sharing.
Oh, let me check. Sometimes we do get undergrads as well, but mostly it's under uh, graduate and faculty.
Okay.
You should be able to do now.
Okay. Nice. Uh, can you see my screen?
Yeah, looks good.
Okay.
Okay, maybe we'll just wait until 10 or 10:01. People are still in
Sure.
the waiting room. Yeah, looks good.
Sure. Is this a summer seminar or
Yeah, so we generally
conference?
try to do every 2 months a seminar on AI for social good. So not
Mm,
necessarily a summer one, but I think it just goes on every 2 months.
I see. I see.
Okay, I think we got people are coming in. We'll probably wait for 1 more minute, Dong, and then we can get started.
Sure, no problem.
Okay, maybe we'll get started while people will keep coming in. So, thank you everyone for joining for this AI for Social Good seminar. Today we have a very distinguished speaker, Professor Dong Wang. So, Professor Dong Wang is a professor at the University of Illinois at Urbana-Champaign in the School of Information Sciences, where his research focuses on social sensing, human-centered AI, and big data analytics. With over 200 peer reviewed publications and three influential books, including his most recent work on social intelligence published in 2025. His innovation in social computing have been widely adopted across academia, industry, and government labs. A highly decorated scholar, Dr. Wang has received the NSF Career Award, the Google Faculty Research Award, and several prestigious Best Paper honors from conferences such as SONAM and ARTAS. Beyond his research, he is an IEEE senior member who contributes to the field as an associate editor of the IEEE Transactions on Big Data and other leading journals. Of course, there's a lot more I can say, but over to you, Dr. Wang.
Thank you, Prof. Yeah, hello everyone. Good morning. Thanks a lot for coming to my talk. Yeah, it's a great pleasure for me to present my work on harnessing the power of a crowd for human-centered computing AI system in this AI for social good seminar. So let's just get started. Recently, an era of human-centered computing AI started to emerge, where human people play critical roles in the computing and AI systems. So here are some examples. First, with the advent of large information dissemination opportunities, like online social media or other platforms, people start to generate, propagate, and consume information from these platforms. So in this scenario, it's important to understand humans' behavior, intention, and connection to obtain reliable and relevant information from these potentially embedded human sources. Second, online crowdsourcing and collaboration systems have also now become a scalable and economic way to address some of the world challenging problems by exploring the wisdom of crowd. Examples include building the worldwide free encyclopedia, addressing some world challenging problems, and creating large-scale annotation data set use crowdsourcing platform like Amazon MTurk or Prolific, and collaborating on some open source AI machine learning project on Hugging Face. Thirdly, both academia and the industry have launched grant initiative on human-centered AI. Example include the Stanford Human-Centered AI Institute and Google's AI for Social Good program. The goal of this effort is to really understand the human needs and roles and build the human-in-the-loop AI ecosystems to address some societal challenges and improve people's life. Last but not least, there is a vision of building the smart home, city, and smart planet by fully exploring the power of smart computing technologies and their interaction with humans who live in these environments. Some example include White House Smart City Initiatives and NSF Smart and Connected Community Programs. So among these recent advances application initiatives, human play a critical role. We believe in a large category of current and future computing AI systems, human will be a key element. We refer to such system as human-centered computing AI systems. So in these human-centered computing AI systems, humans are not only the passive users of such systems, they can also actively participate and contribute to the systems by exploring their own capability or the resources they own from three major aspects. For example, on one important dimension, the capability of human is sensing, where we can collectively report our observations about events that happen in the physical world in a versatile and scalable way. In addition to the sensing capability, our human also very good at many intelligent tasks, such as the tasks that require creativity and social skills, and can often perform them better than machines. Furthermore, there exist billions of individual-owned computing devices where the collective computing power is greater than the world's fastest supercomputers. However, these powerful capabilities of humans have not been fully explored yet. So an important question I ask in my research is how to fully harness the power of crowd by building this human-centered or social sensing intelligence and computing system. And this leads to the overview of my research program. So in my research, I develop both analytic frameworks and as well as real-world systems to address some fundamental research questions to explore humans' capability in the sensing, intelligence, and computing dimensions. For example, in the sensing thrust, we try to address the question of how to use humans as reliable sensors that can help us reconstruct the state of the world, both physically and socially. In the intelligence dimensions, we investigate the question of how to actively integrate human intelligence with AI to fully explore the collective strengths of both human and machines. Finally, in the computing thrust, our goal is to develop a human-centered edge computing system that can fully unleash the massive computing power of individually owned devices to support the implementation and deployment of the human-centered computing AI systems. So in this talk, I'll primarily focus on the sensing and intelligence thrust. In particular, I'll discuss two social sensing system, fog sense and smart water sense in both information and physical space, respectively, and also a social intelligence system called Deep Cloud. So let's get started with sensing thrust first. So for the social or human-centered sensing, we coined the term when we started the research on this direction more than a decade ago. So sensing is broadly defined as a set of applications where data collected from human sources or devices on their behalf. As you can imagine, this really includes a large category of applications such as using X or Twitter data to predict the stock market, and using the Waze app for smart transportation, or use online social media to obtain real-time situation awareness in the aftermath of disasters, or geotagging a smartphone app to identify invasive species in the environment. So one key component, or three key components are tightly integrated in the social sensing concepts. They are basically humans are using the cyber devices to report their observations about the physical world. Okay, so in the following talk, I will illustrate our work in the social sensing thrust using two case studies. One is a fog sense that pretty much done in the information space, and the other is a smart water sense system that is done in the physical space. So let's start with fog sense first. So our fog sense system is really motivated by the current trend of associate multi-model data, or in particular image with your posts on social media. Here are some example of such posts on different type of social media. So such posts are observed to attract more attention than traditional text-only posts. For example, on X or Twitter, the tweets that with images get more clicks, more likes, and more retweets than the tweets without images. Similar phenomenon have also been observed on other type of social media platforms. So while this image content is more engaging and intuitive for these online users than the plain text, but if they are not used appropriately with a post, they can also lead to deliver wrong information of the event they try to describe. So here is one example. So the post on the left is showing some serious event is going on in Paris, evidenced by the picture. However, the reality is something look like shown on the right, right? It's just a group of photographers who are trying to take these exaggerated pictures of the peaceful protest event that happened in Paris. Clearly, the post delivered the wrong information to the viewers. So we refer to such posts as photography, where both the images and the social text convey the questionable or false sense of the event it seems to describe. So the key question here is how to accurately identify the photography and stop the false information spread caused by such posts. However, detecting the photography is not a trivial problem. Here are some examples to illustrate these challenges. So let me show you four additional posts. Um, so basically, the image part of the post is showing on the left, and the text part of the post is showing on the right. So let's start with a simple one. If you look at post A, it basically showing Putin is putting Obama's tie. Clearly, this is photography since both the text and image are fake. So this is the easy case. So now let's look at B. It says sea creatures are falling from the sky in China during a powerful storm event. Do you think this is also photography? Yeah, the answer is yes, but the reason is the image is Photoshop, it's a fake image, but the story is true, right? There's real such events, and if you want to look at the images from the event, here are some examples, right? So you do see some sea creatures on the windshield after a strong storm. Okay, so now let's look at the next one. The post says a guy was waiting at finishing line to propose to his girlfriend, who unfortunately lost her life during the Boston Marathon bombing event. As you probably guess, this is also a photography, but the reason is different this time. The image is real. It's from the event. Nobody added or photoshopped the image, but the story was made up just to attract people attention. Unfortunately, to the sad event during sad event. So now let's look at the last one. The post D says a wildfire is happening in Tennessee, and give you a picture showing that. So, do you think this one is photography? Yeah, looks real, right? So I can give you a little more information. I can tell you both the image is real, it's true image, nobody added it, and the story, short post story is real. There is real wildfire happened in Tennessee during that time. But the 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 end story of this is still this is a photography. And you may ask why? How could a post have both the true image and true text become a photography? And the reason is because somebody borrowed an image from a different forest fire and associate with a Tennessee forest fire just to again exaggerate the severity of the first fire in Tennessee. But if you are really from the area in the southwest part of the states, you'll find that the trees you see in the pictures are normally not the trees growing in that part. It's image bought from Washington State, basically in the northwestern part of the states. So these trees are normally not there. But for people who do not have that local knowledge expertise, it's really hard for them to identify this as photography. Okay, so what are current solutions that can be used to address this kind of problem? Well, the current solution are made in three categories. The classic one, the first category is about the truth discovery or fact-finding tool from data mining or machine learning communities that focus on detecting the false claim from the textual content. However, a major limitation of this type of solution is that they completely ignore the information in the images, right? It failed to capture the photographer pose whose false information is mainly embedded in the images or association between the image and text. So that come to the second category of the approach, which is about the fake image detection developed in the image processing or vision communities that focus on identify image forgery in the post. However, this type of approach are also subject to the failures of detecting the false information and from the text part or association between the text and the image. Okay, now with this multi-language model or large vision language model, they can also be potentially leveraged to address this photography problem, as you can put both the text and image to this model and infer whether the post is photography or not. However, this approach often also have its own limitations. They fail to capture, for example, the incorrect relation between the image and the text, like the wildfire example I just showed you earlier. Also, it is sometimes challenging to generalize these approaches across different application domains or addressing new manipulation methods without retraining the large models, right? If there are some new or emerging events the model have never seen, that do not have examples, probably still very challenging for them to identify photography. Well, so then we ask ourselves, how can we address this problem? We found a common limitation of all the prior approach is they are all content-based. No matter you look at the text part, you look at image part, you look at them together, you look at the content, right? So in order to address this fundamental limitation of the current solutions, we designed a completely different type of approach that does not look at either the text or the image content of the post. Then what do we do? Instead, we focus on the crowd comments of the post to identify the photography. So our tool is called the FoxSense. Here is one example of the octopus pose I just at the time of developing this tool. The FoxSense is the first kind of content ignoring solution to address the photography detection problem in social sensing. And the content ignoring nature makes it robust against any sophisticated uploaders who try to intentionally craft false text or modify the presentation of the images. So before I show you the details of our solution, I'd like to show you a quick demo of our FoxSense tool. Basically, when you find a posts that are suspicious of online media, then all you need to do is copy the URL of that post to our FoxSense or FoxBasker tool. Then our tool will create all these comments from the users who read the post and make a prediction. In this case, we predict it's a photography. And you can see these are the comment from the users, and these are the common network we construct from the users, which I will elaborate shortly. And later, we also independently verify this post as a false claim. Because there's another example which also looks very suspicious. And we do the same thing. We copy the URL of the post to our tool, and our tool will grab the comments of this post. And in this case, prediction is a little surprising. It's not a photography. And if you look at the user comment network, you'll notice that this is somewhat different from the one you see on the photography post. And later we'll also verify this is actually a real post, which is kind of not very expected. Uh, Okay, so now let me show you more details how we build our FoxSense tool. So stay at the core of our design is a user comment network constructed from the user comments of the post. In particular, we construct a network that can be represented by a graph as follows. So first we create a source node S to represent the posting user of the original post. Then we generate another set of node to represent the user who comment on the post of the source user, and the links between the commenting user and the original posting user represent the user actual comments. Similarly, we can define additional layer of user who comment on the comments of other users. So using this recursive definition, we can generate a complete user comment network for a given post. So for the constructed user comment networks, we first are interested in the attributes of the network that can help us identify whether the post is photography or not. For example, if you look at the edges of the network, we're interested in both emotion and attitude expressed by the company user in their comments. And for the nodes of the network, we're also interested in the endorsement or aggregated feedback from other users on a particular users. In order to extract these attributes of the network, embed them into appropriate form, we apply some random walk algorithm to explore these attributes in the network. So here are some examples of the extracted attribute network for both photography and non-photography posts. The first one is a network reflect the emotion of users' comments. The graph is color-coded. Yellow means joy, red means anger. We observed the emotion expressed in the photography posts are highly bipolar. For example, you see a lot of joy and a lot of anger. We were first very kind of confused why there could be a lot of joy expressed in the photography post. Then we analyzed those comments. We found that the joy emotion actually comes from the sarcastic comments about the post, and anger often correspond to the debunk comments. So in contrast, we also observed that the emotion from the non-photography post is much more diversified. The second are the attitude network. So we observe that photographer post network captured the echo chamber event you see here, where this often represent a chain of comments that reflect the public debate between users on some controversial topics from the photographer post. Basically, some people believe it, some people don't. Then they have some back and forth debate. Um, in contrast, the discussion pattern for the users in the non-photographer post is much more ad hoc and distributed. Finally, let's take a look at the user feedback network. In these graphs, the size of the vertex represents a difference between the number of likes and dislikes of all comments of a user. Whereas observe that the feedback of photography posts are also is more concentrated on a few hubs, like you see here, um, who that represent user who post some evidence to debunk the original photographer post, such as, hey, this image is fake and here's a URL. So in such kind of scenario, this user normally get a lot of endorsement from other users to appreciate their contribution of identifying and debunking this photographer post. But if you look at the network of the non-photographer post, the feedback is much more dispersed. Okay, so while the above global network attributes are quite helpful to identify the photographer posts. We also found there are some very interesting local user interaction patterns that are quite informative to solve these photographer detection problems. So here are some examples. The first example is the tornado example you see in the demo video. Um, in this one, we identify a very interesting pattern called a popular debunker. Um, if you look at the post of this look at the comments of this post, you can find that there is a user who first identified this photography and debunk it, and after that, there's a group of users in the community show their endorsement and appreciation for this debunking user and by giving them a lot of positive feedback. So this is what we identify as a popular debunker, which is appear a lot of in this photography debunking post. So here it's another example of local interaction patterns we identify. It's called convince user. Here is after example I showed earlier. So if you look at the post of this one, there was a user first read the post and believe this is a real post. And then this convinced user was debunked by another user by providing some evidence. In this case, it's a URL for a template people use to create this fake image. And then this convinced user uh, understood that they made a mistake at the beginning. Then they come back to appreciate the debunking user by thank them. So this is convinced users pattern we identify in the uh, uh, analysis as well. So after we collecting this user common network information from both global and local perspective, we encode the network that capture these attributes with a stack encoder into a set of feature vectors. Then we also integrate these feature vectors with a few additional metadata features and feed them into a supervised classifier to identify the photographer post. Um, for the classifier, we test a set of representative one and pick the best performing one as our final scheme. So here is our result, the RC curve showing the effectiveness of the fog sense. We compare it with a set of state baselines in fake image detection and fake claims detection. We can see that our scheme achieved the best performance in terms of identifying the photographer post while keeping the false positive the least. So one more thing I want to comment on this line of work. We find that this content ignorant approach of our Foxen system is actually generalizable and can be applied in many other problems beyond the photography detection. For example, we have applied this content ignorant approach to identifying the copyright infringing video from online video sharing platform like YouTube by investigating the common networks from the audience of the video and also detecting the harmful vulnerable videos that are likely to attract harmful comments while the content itself in the video is completely neutral and hate-free. I can elaborate more in the QA session if you guys are interested in this line of work, but we believe that this approach can actually further be applied to solve large category information distillation problem by leveraging the wisdom of our crowd. Okay, so with this first example of folk sense in of social sensing in the information space, I like to switch the gear a little bit by presenting another example of the social sensing system we developed called Smart Water Sense in the physical space. Okay, so this work is motivated by the fact that groundwater quality is a critical environmental issue nationwide in the United States. Currently, more than a third of the US population are actually relying on the groundwater as their primary source of the drinking water, and this number is roughly 150 million, right? So, however, the groundwater sources are pretty vulnerable to contamination introduced by human activities. For example, the agricultural fertilization and uncontrolled waste disposal can contaminate the groundwater with excessive amount of harmful chemicals. Among these contaminations, nitrate is an important widespread contaminant in the groundwater. There are roughly about 6 million Americans who are suffering from the high nitrate contamination, which can cause serious health issues such as cancer and birth defects. So as part of the groundwater dependent communities, the campus of our university and also our collaborators are located in the areas with high risk of the nitrate contamination. So that motivate us to really study this underground water quality monitoring by using some smart technologies we can develop. Okay, so what's current solutions? However, in the United States right now, there often lacks effective government regulations on the groundwater quality monitoring. For example, there's no regulation on the quality of groundwater from private wells in many well-dependent communities. And more importantly, the residents in the well-dependent communities are often aware of the health risk introduced by the groundwater contamination. They may likely consume the contaminated water without knowing what's in the water. So it's really necessary to develop an effective solution to not only estimate the contamination, but also increase people's awareness of the drinking water safety issues in the community. So currently, the groundwater monitoring solutions mainly rely on the groundwater properties measured at the groundwater sampling sites. Such solutions will require the installation of the sampling equipment. In addition, they also need professional groundwater collections and also the high quality measurements from the lab. So it's basically a very expensive and time consuming process that is not scalable to large communities. So motivated by these limitations of these solutions, in this work, we study the crowd sensing-based groundwater nitrate estimation problem that can be deployed in the smart and connect communities. So basically, crowd sensing is a new data collection paradigm that can obtain the measurements from non-technical individuals, which can address the scalability and efficiency problem associated with a conventional water sampling approach. So in our work, we consider the residents at the well-dependent communities as a crowd sensors to collect the crowd sensing nitrate data. Our crowd sensing approach is infrastructure free since it does not really require any installation or maintenance of the physical sensors. Instead, it only utilizes some affordable test strips to approximate the nitrate concentration in the groundwater samples, which I will show you a short demo soon. In addition, the crowd sensing strategies can also actively engage the members in the well-dependent communities to monitor their groundwater quality and also get informed about their drinking water safety issues. However, there are two technical challenges involved in developing these crowd sensing based solutions. The first challenge lies in the data reliability and the spatial irregularity of the crowd sensing nitrate data. First of all, we know the crowd sensors are humans. They are not necessarily as reliable and accurate as the physical sensors. They can make mistakes and inaccurate measurements, or sometimes even forget the crowd sensing data completely. Secondly, while the physical sensors can be easily programmed to collect data at specific time and locations, crowd sensors may contribute data with a much more irregular spatial patterns. For example, if you look at this nitrate contamination uh, heat map and compare with the population density map with Indiana, you observe that the places with the highest population density are not necessarily the places with the highest nitrate contamination. So existing spatial estimation solutions, they mainly rely on the groundwater property that are measured at fixed water sampling stations, which are predefined based on the regular geographic grid. But such a grid-based approach ignores this uneven residential density, and also they cannot be applied to model the spatial irregular cross-sensing nitrate data. We'll also observe that there are high, um, yeah, so basically the key question we ask here is how can we extract the spatial relations among these regular, potentially unreliable crowd sensing data from the crowd sensors? The second challenge lies in the hidden temporal dependency of the groundwater contamination on the anthropogenic context. So here are some examples. The nitrate concentration in the groundwater sometimes is often correlated with some temporal dynamics of our human activities. For example, you may have lawn or pets in your household, and the seasonal fertilizer application can also dynamically introduce nitrate to the groundwater. Similarly, Now, we need to consider how to address this challenge of capture the hidden temporal dependency of the anthropogenic context um, to accurately estimate the groundwater nitrate concentration while we're using the crowd sensing data. So to address these challenges, we developed a smart water sense, a graph neural network framework to accurately estimate the groundwater nitrate concentration. In particular, we collect the crowd sensing measurements and the corresponding anthropogenic context from the participant in well-dependent communities. And the collected data was then used to construct a graph-based crowd sensing network to explicitly model the spatial temporal relations between the crowd sensing data points. Then we design a context-aware network optimization strategy to accurately estimate the nitrate concentrations. So due to the time of the talk, I will not elaborate the detail of the solution, but I'm happy to talk more offline. So to validate the proposed smart water sense framework, we carried out a real-world case study in St. Joseph County in northern Indiana. Northern Indiana, as you can see, is an area that represent not only a significant amount of agricultural land use, but also a large number of well-dependent households. More importantly, it is also a high-risk area of the groundwater contamination. To recruit the crowd-sensing participants, we partnered with the high school residents community through the university outreach program. We leverage this participant recruitment opportunity to engage the local residents and increase their awareness of the nitrate contamination in their drinking water. So here are some pictures of the events we have held during the recruitment process. For example, we developed several tutorials and mini lectures that can not only teach the students about the data collection process, but also can be integrated, excuse me, can also be integrated with their curriculum in the environment science and biology classes. So to collect the crowd sensing data, we distribute the nitrate test kit to our participants. Here's how the test kit looks like. So each test kit contains a test tube and to collect the groundwater samples and set up test strips to measure the nitrate concentration. Also has a colorithmic chart. It is used to approximate the numerical value of the nitrate concentration. So this is very similar as a pH test. If you still recall from your chemistry class. We'll also provide a very short video for you to have a sense how the sampling is
full
done.
of test strips and take one out. Head it and set it somewhere dry. Take your dipping only test tube and fill it with bathroom tap water. We're going to dip our one test strip into the test tube for 2 seconds and then pull it out. Now go ahead and take your nitrate colorimetric sticker and compare your nitrate test strip by using the top color pad to the top row of colors.
Yeah. And finally, we also provide the tutorial video on our website and develop this both web-based and smartphone-based application for people to easily contribute their data once they're finish their test. So in addition to the crowd sensing data, we also collect the ground truth water samples from the participant and measure the ground truth nitrate data at the university laboratory. So here are some photos of our uh, labs and the equipment we use. And finally, here's a heat map of the nitrate concentration of the ground truth data we collected from our communities. By looking at this data, it's really verified there does exist non-trivial nitrate contamination issues in the communities we carry out experiments. Okay, so to validate our work in the first set of experiments, we study how accurate the smart water sense estimates the nitrate concentration based on crowd sensing data. We compare our smart water sense framework with set of state-of-art baseline in machine learning, GIS, and deep learning. Based on the result, we observe that our system outperform all the baseline by achieving the lowest score in these error metrics which shows the effectiveness of our framework to accurately estimate the nitrate contamination by using the potentially noisy and incomplete crowd sensing data. What we're particularly excited about this project is after 2 years of implementation of our project and sharing our result with the local government in the Granger, which one of the city we implement our smart water sense framework. um, they decided to implement the change from the private well water to the treated public water system, which is a huge change and decision for the local community because from then on, the community can no longer worry about their nitrate contamination in the groundwater because they start to use the public water systems. So that also demonstrates the contribution of our project to improving the drinking water quality in our local communities. Okay, so now I have shown you two examples in the social sensing space where human or crowd are primarily acting as sensors, which they simply share their observations independent of data processing and analytical tasks. In the second thrust of my research, social intelligence, we focus on another challenge question, which is how to actively explore the human intelligence and integrate it with AI techniques to fully harness the collective power of both human and machines. So in the remainder of the talk, I will give you one example of this dimension. So in many current applications, human and AI are considered as competitors in a zero-one sum game, especially with recent rise of large language models. There's a concern that AI will replace human workers in the future. However, we take a slightly different perspective on this problem. We believe that human intelligence and AI are complementary to each other in many aspects. For example, our humans are known to be good at the tasks that require the teamwork, that uh, need excellent social skills. But in contrast, AI or machines are generally good at the tasks that require high speed, run at a large scale, or generate very accurate quantitative results. So given such complementary nature or strengths of both human and intelligence AI, we believe that they should actually work with each other hand by hand to finish the challenging tasks that cannot be easily accomplished by either of them. So this motivates us to develop some new mechanism to effectively integrate human intelligence and AI. So in this talk, I primarily focus on a particular application called disaster damage assessment to illustrate our work in this dimension. Uh, for example, in the disaster scenario, some extreme disaster events such as hurricanes or earthquake can strike a community with little or no warning and leave it with a high level of damages. Many of these damages often happen simultaneously at different places in affected area. So a key question faced by the emergency response team at that time is how can you or how to prioritize your team's operations? For example, where should we send the response resource first? So the answer to such question largely depend on the severity of the damage at different locations. So traditionally, the response team depend on the data from emergency call center to collect the damage assessment information on affected areas. For example, during the 2017 Hurricane Harvey crisis in Texas, the 911 emergency lines were overwhelmed by more than 56,000 calls in 15 hours in Houston alone, which greatly exceeds its maximum capacity of 8,000 calls per day. Such approach turns out to be not only not very scalable and sometimes even become the bottleneck of the whole response systems. So in such cases, people just resort to using social media to ask for help and share their updates. For example, some people post their flooded house on social media and send a message for help. So given this rich set of self-reporting data, a new application called Cloud-Based Disaster Assessment or CDA start to emerge. So in these CDA applications, the witness of disaster, they just send the photo of the damage, saying they take to nearby computing resources. It can be the smartphone, the drones, or cars, which can generate the damage index using some deep neural network-based AI solutions to assess the severity of the damage. The app then sends the damage index to the response sender to prioritize operations. So using AI techniques and real-time data feeds, the CDA application turns out to be more responsive and scalable than the manual efforts. Um, However, the AI-based solution also suffer from some of these multi-failure cases, as shown in the following examples. For example, in the first case, it showed a fake image that was classified by some AI algorithm as severe damage. Similarly, another image here, it just shows a close-up of a crack on the road, but AI algorithm, if they don't have the context they sometimes fail to identify that and misclassify this as a severe damage. In other two examples, the algorithms may also misclassify a severe damage, saying to no damage or mild damage due to either the low resolution, like you see in the C, or just lack of understanding of implicit context in example like D here. However, we observe that human actually can better address these failure cases by leveraging our own background knowledge, the ability to understand the context, and capability to do the reasoning and inference. In the example we just showed, as humans, we can easily infer the damage severity from what we observe, which is not necessarily actually the damage. So a key challenge of using human intelligence in the traditional disaster response application is the fact that human labels are often difficult and expensive to obtain. However, thanks to the online crowdsourcing platforms such as mTurk and Prolific, access to human intelligence become much easier and scalable. Therefore, in this work, our goal is to investigate how to integrate the human intelligence with AI in the CDA application for more efficient disaster response. So to achieve this objective, we designed a deep crowd framework that leverages human feedback from the crowdsourcing platform to troubleshoot, calibrate, and boost AI performance in our application. So here's an overview of the crowd design architecture. So when the CDA application collects a set of self-report images, we first send them to the QSS module to find the optimal set of data samples, query the crowdsourcing platform for feedback. And we also develop a new incentive policy design scheme to incentivize the crowd to provide timely response to the query. Then we send the queries together with incentive to the crowdsourcing platform. After we get the feedback, a crowd quality control scheme is designed to refine the response from the crowd. And finally, we develop a machine intelligence calibration scheme that can incorporate the feedback from the crowd to improve the AI algorithms. The four components are integrated into a holistic closed-loop system that allows the AI and the crowd to effectively interact with each other and address the failure scenario of AI we discussed earlier and achieve the boost performance of applications. Okay, now before I show you the details of the audio, I also show you a demo of the deep crowd. So when you have some damage images, you are not sure its damage level, you can put into a scheme first. The ground truth is severe, but the prediction is wrong because we don't integrate the crowd intelligence. The second one, we start to incorporate with the crowd intelligence and the prediction becomes correct. Here's another example I showed earlier, and you just put into our tool. First, we show the case without crowd, the prediction is incorrect. And the second time, we choose to integrate the crowd. And the prediction is correct this time. Okay, now I will dive into some key modules of the deep crowd system to show you some more detail about design. Due to time limit, I will not be able to go over each of the modules, but I'll pick two just to give you a sense. So let's start with query, the first module, query set selection. In crowdsourcing, it is often impractical to send all the data samples for the crowd to label due to the budget and time constraints. To identify the query set, the key strategy is to identify the data sample that an algorithm is uncertain about. Here, example of our scheme. So an image is an input to our system. We have a committee of AI algorithms, and each of them will classify the image across all possible damage levels with different confidence scores. For example, A1 equal to 0.5 here means algorithm A1 has 50% confidence to classify the image into the severe damage class. We treat the classification scores as the committee votes for the AI algorithms of the image across all possible candidate classes. Based on the vote, we can actually compute some entropy of the committee based on their for the decision of the image. The higher the entropy is, the less certain the AI algorithm are about the result. So here is another example of the images where the committee have relatively high confidence and high consensus, so it has lower entropy of the committee. So given the entropy of each data sample, the intuitive strategy is just pick the data sample with the highest entropy for the crowd to label, because the other schemes, the other post AI algorithm are not sure about. However, such strategy would fail when all AI algorithms happen to report the same result, same wrong result. For example, if all AI classifier fail to capture the fake images and report the fake image as severe damage with high confidence, then the QSS module will never pick up the fake images for the crowd to check. To address such problem, our module also has to occasionally include some data samples with low entropy. This turns out to be ex, exploration versus exploitation problem, and we use epsilon gradient algorithm to address this problem. So finally, after we get feedback from a crowd, we also integrate them with AI modules through this MIC model. Now we have the feedback. We'll compare the output of the crowd with different AI algorithms. Based on the discrepancy between the crowd label and the algorithm output, algorithm will be rewarded or penalized by increasing or decreasing its weight. The algorithm with a higher weight will play a more important role in the committee for future tasks. Then we update the weights based on the feedback control mechanism, use exponential weight updating schemes. Since the crowd label are often more reliable, then we also use them as extra training data to further retrain all the AI algorithms to improve the models. In short, the first strategy is meant to address innate flaws of the AI models, and second strategy is meant to address issue of the training data, and they work together to boost the performance of our CDA applications. And finally, here's the result of the deep crowd system. We compared it with a few other baselines, and including both pure-based AI solution or human AI hybrid solutions. And we found the deep crowd outperformed this baseline by effectively integrating human intelligence into the AI systems. Final note on this is here are some other examples of the applications that can also benefit from the integration of human intelligence AI. For example, the expandable medical AI system, the new human-centric AI system will not accurately diagnose the disease by exploring the power of AI, but also offer the reasoning and rationale of the diagnosis by exploring the expertise or experience of the doctor. Many other similar systems include the AI-assisted design, AI for art, or ethics, fairness, or responsibleness in the AI. So now we have discussed social sensing intelligence thrust. The next question we may want to ask is how to implement and deploy this human-centered application in a scalable and efficient way. So that relates to the third thrust of the research on the human-centered computing thrust, which we will not have time to elaborate today, but happy to discuss it after the talk. Okay, so there are a few other projects in my lab that happen on the three different dimensions. For example, in the social sensing dimension, we also study how to use social sensing to understand some environmental impact like the drought, or use a social media integrated with drone system for disaster response. On the intelligence system side, we also study the fairness and privacy issues for human-centered AI system for education and information alignment problems. And for the computing side, we also study some AI at edge problems and further learning issues and so on. So in the long run, we believe that social sensing intelligence and computing paradigm will be translational, impactful in the sense that it can directly contribute to many real-world applications that can help us save our money, save our time, and even save our life in the disaster scenarios. Also exploring the computing power around us to make our environment more intelligent and comfortable to live. And all these will help to realize the grand vision of smart planet, where we can harness the power of humans and machines to make our world a better place to live. Also, my research generates three books. The first book is on the dimension of social sensing, published by Elsevier. The second book is on the dimension of social edge computing, And the third one, the most recent one, we talk about the social intelligence by integrating human and AI together. Um, I like to conclude the talk with my long-term vision as to build this reliable and optimized human-centered sensing intelligence and computing systems, which is a very interdisciplinary area. I see it as an intersection of three major trends: the interactive computing, the AI, and social good applications. So at the center of this research vision is human. Here are some example of the potential overlap of different areas of my research vision. There are many exciting problems. I look forward for collaborations. So if you are interested in some of these intersections, please feel free to reach out to me. At the end, I'd like to acknowledge funding agencies and the great work done by my postdoc, my students, and also my great collaboration with my collaborators. With that, I'd like to conclude the talk and take any question you might have. Thank you.
Thank you, Dong, for a very, very, diverse but a very, very impactful talk. Like the areas that you address are phenomenal in terms of, disaster and water quality. It's amazing. So I will open it up to the floor for any questions if anyone has. You can just unmute yourself, speak your name, and maybe just get started.
Hi, Professor Wang. I am Arath. I just wanted to know what exactly did you mean by anthropogenic context, and how did you collect that, and how did you address the uncertainty in the collected data that you were getting from the crowdsource?
Yeah, that's a great question. Let me come back to that slide so I can show you more details. Yeah, so for this one, as for organic context, we mean the context that may affect the nitrate contamination. For example, have you applied the fertilizer in your lawn? Do you have a lot of like pet activities in the lawn which may affect the nitrate contamination groundwater? Or are your household is close by a farm? We found a lot of household close by a farm will be affected by the application of fertilizer or pesticide or even farm animal waste. So this is what we mean by anthropogenic context, where they are mostly related with human activities, right? And to address the question how we collect it as part of our crowd sourcing experiment. Remember, we developed this smartphone app or web portals. So when people enter their crowdsourcing data, we also ask them to enter this anthropogenic context information when they send me their data. So this is how we collect it. I think you also talk about this uncertainty in the crowdsourcing data. Yes, that's definitely one of the fundamental challenge in the social sensing, not necessarily only to this application. So we developed a set of theoretical framework to address data reliability issue in crowdsourcing applications. So one intuition for what like one category of this approach is to create this bipartite graph. On one side of the graph is the node represent the crowd sensors, basically the human participant. On the other side of the graph, the node represent their measurement or their reports. Then the link in the graph describe who contribute to what, right? If there is a link between the source node and the claim node, that means this participant or source make that observation. And you can imagine this graph, the links tell you a lot of information. For example, if a lot of source tell you pretty similar information, that claim get relatively high credibility. On the same side, the source who have linked to that high credible claim have the higher reliability. So in the end, at the end of the day, it's kind of iterative algorithm to estimate both the source reliability and the claim credibility with minimum prior knowledge. So that's one type of approach to kind of mitigate the source reliability issues. Another more practical approach to address the data reliability issue is to have training for your participant before they join experiment, right? Don't just let them start from nowhere. Offer some tutorial, invite them to workshop, show them some demos, lets them do some test trials before they start to actually do the measurement and give you data. We observe there is a significant improvement in the quality of the crowdsourcing data after this kind of training process. Yeah,
Thank you so much.
Thank you.
you're welcome.
In fact, I have a very simple but a very interesting question on this one, Dong. One of the key challenges that I
Yeah.
always find with participant-based research, and especially when you're trying to do crowdsourcing, is an adoption.
Hmm.
When you have a technological solution, let's say your water contamination problem, how do you
Hmm.
how do you go about ensuring that your participants actually adopt the technology first in the place for developing the solution, and then of course after that as well? How do you, like, that's to me is a more practical challenge of adoption and community engagement.
Yes, yes. I think thanks a lot for the question. That's a critical part of the crowdsourcing experiment, how to make sure people actually adopt your technology and also use it, right? Use it throughout the experiment. They don't just try and keep up immediately. So my kind of experience is first make your technology simple, right? Don't make it too fancy or overcomplicated than it should be. So for example, in our crowdsourcing experiment, we use a test strip, which is very similar to the like a pH test. Anybody can uh, understand and do it after a short tutorial. So make it simple. I think it's very easy. It's very important steps. And second one is to really find a smart mechanism where you can keep people engaged. I will give you one example. In our case, rather than just lock the door of this resident in this community and ask them to participate, we choose to go to the school systems. Basically, we reach out to the school, high school or middle school system through their chemistry teachers because we feel there is a strong connection between our research and what they offer in the curriculum. If you can build that connection, integrate your research with their curriculum, then it's much more likely it's the students who are participating in our case will do it because that's part of their homework. And of course, we provide some like a gifts or provide some incentives in terms like books, right? So to kind of reward people who give good result. But if they feel they can learn something from your experiment, they will normally get engaged and stay throughout the experiment. But people always drop out, right? No matter what you do, you'll never get 100% participants throughout the experiment. That's part of our research. That's why we developed some scheme to mitigate these missing data problem.
Oh, excellent. No, that's absolutely fantastic. Yeah, that's a very common problem, but that's also a very important point to keep in mind when doing any community-based research. So, thank you. I know we are out of time, so if anybody else has any questions, you can always email me and or directly Dr. Wang. I will make the recording of this talk available to the participants after. But again, let's thank Dr. Wang for a fantastic talk, very impactful work, and looking forward to connecting with you, Dr. Wang, in the future.
Thank you. Thank you so much for your time, and thanks you for coming to my talk.
Thank
Yeah,
you.
stay in touch.
Bye.
Bye.